Hello friends, welcome to the molecular weight distribution and addition polymerization, that is a chain reaction polymerization under the edges of chemical reaction engineering in polymeric systems. So previously we have discussed about the self-catalyzed step growth in the gel point, the molecular weight distribution, molecular weight control. They discussed about the quantitative aspect of molecular weight and molecular weight distribution. In this particular lecture, we are going to cover the molecular weight distribution which we left in the previous lecture. Then we will discuss about the addition polymerization. Apart from this, we will discuss about the radical chain polymerization, and we will discuss about the overall rate of polymerization and gel effect in addition polymerization. So let us talk about the molecular weight distribution in non-linear polymerization using over two reactives and group such as tri and tetra functional monomer. This produces the step polymerization of non-linear polymer molecules such as overbranched or cross-linked polymer and dendrimers or dendrigraft polymers, which you can see like here you are having the dendrigraft polymers, then dendronized polymers, then hyperbranched polymers, and these are the dendrimers. Now, the functionality play a vital role. So let us talk about the effect of functionality. So the multifunctional monomer molecule, they can have a specific type of functional groups like A3 or various forms of group like AB2. So the average functionality, that is F average of the for the analysis of polymerization kinetics for multifunctional monomer is defined as the average number of functional group per monomer molecule, and that is F average, that is equal to summation of Ni over summation of Ni, where Fi is the functionality in the reacting mixture of monomeric species, and this is represented as equation number 9. Now, the polymerization of a vinyl or related monomer M induced in presence of a free radical initiator. So, the I, this is I, which I is the initiator. This may be expressed as like initiator decomposition. So, I, that is Kd first, this is the initiator decomposition. Then we start the chain initiation. This is Ki R Mi. Then again the chain initiation for other components. This is Rm1, then M, Kp, sometimes referred as propagation because the formation of different chains. Then Rm2, Kp, Rm3, then Rm in a generic term plus M. This is the chain initiation, and then we may have this Rm in a generic term this the formation of the polymeric chain. This can be KTC and another one can be Rm and Rn, and this can be KTD. Now, in the non-stoichiometric, that is Na is less than Nb, no reaction can take place after the A group. This is fully finished, and it is the convenient to think that a limiting functional group instead of the total conversion. So, in that case, the average functionality can be defined as the total amount of functional groups that can react, and that is divided by the number of molecules initially present in the system. Now, from this equation, the dPn, which we have already discussed in the previous lecture, tends to infinity as P is equal to 2 over F average. Therefore, if this F average is greater than equal to 2, the limiting functional groups, the conversion is reasonably high and the average chain length of the number becomes infinite and the polymer gelation occurs. Let us talk about the addition polymerization. Addition polymerization is the process by which unsaturated monomers are converted to the polymers of high molecular weight, exhibiting the characteristics of a typical chain reaction. So, a large number of different class of unsaturated monomers such as ethylene, like CH2 double bond CH2 is the simplest olefin. Alpha olefins CH2 CHR, where R is an alkyl group, vinyl compound, like CH2 CHX, where X is either chlorine, bromine, iodine, alkoxy. These are the conjugated diolefins mechanically characterized as a chain growth polymerization or simple chain polymerization. Now, they are the addition or chain growth polymerization are the fast reaction typified by three different distinguishable steps. One is the triggering off, that is the initiation, second is the propagation, and third is the termination step. The initiation is usually a direct consequence of generation or introduction of highly reactive species that is referred as R naught through the dissociation or degradation of some monomer molecules as a consequence of a dissociation or decomposition, which we can be represented as I can be dissociated or can decompose to R ionic. Now, the reactive species, this may be a free radical, cation, anion, whatever, which readily attacks the unsaturated monomer molecule if the conditions are favorable, adds itself to the monomer molecules by opening. The reactive species may be free radical, cation or anion, which readily attacks to the unsaturated monomer molecule if conditions are favorable, adds itself to the monomer molecule by opening a pi bond to form a fresh reactive center, that is a radical, cation or anion, depending on the nature of the radical and prevailing the chemical environment. The new reactive centers, they add to another monomer molecule M, and the process is repeated in quick succession, leading many more monomer molecule to add to the same growing species at its reactive or growth centric to carry out on the propagation of the chain process. Now, here let us discuss about the termination, because we have discussed the initiation, decomposition, initiation in the previous slides. Now, let us talk about the termination. This is these are the radicals and CH2, CHX, CHX, CH2, R. Now, termination by disproportionation reaction, which we discussed earlier, that is R, CH2, CHX radical plus radical CHX, CH2, R, KTD, CH2, CH2X plus R, CH, CHX. For vinyl monomer M, let us take the structurally written as CH2 double bond CHX. The growing chain of size N may be structurally written as like this. So, the chain growth is terminated at some point by an appropriate mechanism, largely depend on the type of the reactive center, that is radical, maybe cation, anion, and the nature of the monomer M and the overall environment condition of the reaction. So, on the basis of steady state assumption, this radical M, this may be expressed as FKD over KT to the power half. The expression of the rate propagation RP, because initiation, propagation, termination, these three are the steps, this can be represented as Kp over Kt to the power half FKD to the power half I Let us say this is equation 3. Now, where R is, this R is the free radical generated from the initiation or initiator RM1 radical or RM2 radical or RM3, etc. They are the growing polymer chain and each bearing a free valency of the radical center at the chain end. And RM, RMN, Mn, all these things are the dead polymer molecules which are obtained. That means they cannot further grow. So, a common feature of the vinyl polymerization is that the active center of the kinetic chain is retained by a single molecular species throughout the chain growth or chain propagation process. So, the fact is that the polymer molecules formed in the early stage of reaction are usually comparable in the molecular weight or chain length to those formed at a much advanced stage of the process. Now, when we talk about the kinetics of chain polymerization using free radical initiation, the chain growth or a propagation reaction involves the addition of a monomer, that is M, or to radical Rm, and to the successive radicals. Each successive propagation reaction is characterized by the rate constant of propagation, that is called Kp, assuming that the radical reactivity is independent of the chain length as long as the end structural segment on which the radical site rests is just the same. So, the all successive propagation step may then be expressed by the general expression, that is m radical plus m Kp m radical. Let us talk about the termination aspect. The termination of polymerization is a bimolecular in nature and it involves the reaction between a pair of a chain radicals leading to a complete destruction of two chain radicals in each incident of the termination reaction and the production of what is known as the dead polymer. The termination is reaction by two different modes. They represent the coupling or mutual combination of two chain radicals characterized by the rate constant Ktc and disproportionation of chain radicals characterized by the rate constant Kdt. Now, here you see that the rate of initiation, this can be expressed as Ri 2Ki M2. Now, considering the bimolecular termination giving rise or giving the rate of termination, that is RT is equal to 2kT m to the power 2, and under steady state assumption giving rise to say Ri is equal to RT, the chain radical concentration may be expressed as Ki over Kt to the power half m. Now, the rate of polymerization Rp is expressed as Rp is equal to Kp m radical into m, which is equal to Kp Ki over Kt to the power half m to the power 2. So, for the kinetics purpose, the bimolecular mechanism of termination alone is important and the exact mode, that is the combination or disproportionation, does not make any difference. So, that the termination step may be simply expressed as m radical and m radical, that is Kt, that you will get the dead polymer product. That is two radicals, they can combine together to neutralize the radical charge and they give the dead polymer. Now, here this Kt is the overall rate constant of a bimolecular termination and which is referred as Kt is equal to Ktc plus Ktd. Now, let us talk about the rate of chain initiation. Now, decomposition of lone initiator, it involves the homolytic cleavage of a weak bond in the molecule such that the chain initiating radicals are generated in pairs. Now, here Rd is the rate of initiator decomposition. This may be expressed as Rd is equal to minus di over dt is equal to Kd I, concentration of I. The rate of radical generation d concentration of R over dt, this would be the radical R d over dt equal to 2 kT concentration of I. Now, as the radicals are transient species and they give rise to the chain initiation as soon as they are generated in the monomer system, the rate of chain initiation Ri will be the same as the rate of radical generation in the absence of undesirable wastage of the chain initiating radicals R by side reaction. So, this can be represented as Ri is equal to d radical of m over dt is equal to Ki, concentration of R, concentration of M is equal to 2 Kd concentration of I. For Ri, this is the 2 Kd I. This makes the ideal case, that is 100% efficiency of the chain initiation by the primary radicals. Now, for all practical purposes, however, the expression is modified as Ri is equal to 2 FkdI, for where the factor F, this factor is the initiator efficiency or the efficiency of the initiation. This is represented by the fraction of primary radicals which actually contributes to the chain initiation. So, the value of F is less than unity due to the side reactions leading to the measurable wastage of primary radicals. Now, F will be dependent on the monomer concentration M. If the wastage R is high due to side reaction, and in that case Ri should be dependent on concentration of monomer. The rate of overall termination RT, this may be expressed by this particular reaction, considering the termination reaction in a simplified and a general form as per the reaction mechanism, and thus mathematically we can represent as RT is equal to minus D concentration of M monomer over dt is equal to 2K concentration of M radical to the power 2. The factor 2 is used for the simple reason that each incidence of a termination reaction, 2 chain radicals disappears, like this one. So, it is important to note that the radicals are generated in pairs, they are also destroyed in pairs, otherwise one active radical will be there. Now, rate of propagation, now considering the chain propagation reaction in the general form, the rate of propagation or the chain growth Rp, this may be expressed as Rp is equal to Kp, M radical and concentration of M. This equation is not directly useful for the evaluating the rate of propagation, as it contains the term for the concentration of transient chain radicals, because the radical concentration are very difficult to measure as they are very low, and that is maybe 10 to the power minus 8 mole inverse. So, if we talk about the overall addition of overall rate of addition polymerization, now steady state assumption is that in order to eliminate the radical concentration term M, it is necessary to find an expression for it in terms of known or measurable parameters. So, as per this assumption, soon after the chain initiation, a state is attained where the value of this M radical become essentially constant or steady as radicals are formed and destroyed at equal rates, that is Ri is equal to Rt. So, on the basis of the steady state assumption, the concentration of M radical, this can be expressed as F Kd concentration of initiator over Kt to the power half. This can be represented as equation 2. Now, the expression for rate of propagation Rp, this reduces to Rp, that is equal to Kp over Kt to the power half Fkd to the power half into initiator concentration to the power half into M. So, this can be represented as equation number 3. So, by this way we can represent this both concentration of M radical and Rp. Now, if we talk about the overall polymerization, now examining the overall scheme of polymerization, this shows that the monomer disappearance takes place at a chain initiation and chain propagation steps only. Hence, the overall rate of a monomer disappearance, that is d minus dm over dt, which is the same as the overall rate of polymerization, this can be expressed as minus dm over dt is equal to Ri plus Rp. So, as the number of monomer molecules consumed at the initiation step is far less or insignificant compared to the number of consumed in the long sequence of reaction in the propagation step. So, the overall rate of polymerization is for all practical purposes simply equated to the rate of propagation, that is Rp. Therefore, overall rate of polymerization can be given as minus dm over dt, that is equal to Rp Kp over Kt to the power half Fkd to the power half I to the power half and concentration of monomer. So, if we club equation 3 and this equation, this can be represented as Rp is equal to Kp over Kt to the K to the power half into 1 by 2 R I to the power half into concentration of M. Let us talk about the gel effect in the addition polymerization. The reaction medium transforms fast into the highly viscous mass due to increase in the reaction rate. The sharp rise in molecular weight of the product polymer accompanying this particular phenomena commonly termed as a gel effect, which is also referred as Norrish-Smith effect. Now, this gel effect is more effectively manifested in undiluted monomer than in diluted system, where non-ideal or unusual effect may be minimized or even eliminated. Now, here in some of the monomer system, the gel effect may be so high as to accompany by the large rise in temperature. So, using undiluted methyl acrylate or acrylic acid or acrylonitrile, the gel effect associated with the polymerization process may even lead to the explosion. And various accidents they do occur in past just because of this gelation. Now, influence of dilution in controlling gel effect percent conversion versus time plot is given here. This is for the benzyl peroxide initiated polymerization of methyl methacrylate at 50 degrees Celsius. You can see the effect in the different domain of the different concentration. So, dear friends, in this particular aspect, we discussed the various aspects of addition polymerization, different effects, and for your convenience, we have enlisted a large number of references. You can go ahead with the further studies as per your convenience and as per your choice. Thank you very much.